Welcome everybody. It's lovely to see all of you on the participants list. So this is our 14th Talking Crystal Growth and Design webinar. One of the good things to come out of the pandemic, I guess, if you can call it that. For those of you that haven't been here before, this is a monthly series showcasing some of the most innovative research in our field. My name's Johnathan Steed. I'm the editor-in-chief of Crystal Growth and Design, and I'm joined by my co-host Len Barber from Stellenbosch University. Let me just start by thanking the American Chemical Society for supporting the series, particularly the ACS marketing manager, Kristen Call, and managing editor, Sonia Crane, for making it happen. They're the power behind all the organization. I just sit up here and pontificate. Before I introduce today's speaker, just a reminder that next month on Wednesday, the 13th of April, at the usual time, so 9 o'clock Eastern, 2 o'clock British Standard Time, we've got Franziska Emmerling from the German Federal Institute for Materials Research and Testing. And she's going to be telling us about mechanochemistry and co-crystals, a never-ending story. And certainly from the symposium I was at earlier in the week, it's certainly a fascinating and growing story. But the main event today is Professor James Wuest from the University of Montreal, one of the regulars on my list in front of me at Talking Crystal Growth and Design, and it's a fantastic honor for us to have him as a speaker today and obviously as a regular participant as well. Jim hails originally from Cincinnati, Ohio. He graduated in chemistry and mathematics from Cornell University back in 1969, which was the year I was born. Jim got his PhD in organic chemistry from Harvard in 1973, working with Nobel laureate Robert B. Woodward. He then stayed at Harvard as an assistant professor before joining Montreal back in 1981. And it's a good advert for Montreal that he's been there ever since. Must be a nice place to live. He's a Canada Research Chair in Molecular Materials and they've been awarded many, many awards in his career, including the Alfred Bader Award in Organic Chemistry and the Arthur C. Cope Scholar Award in 2005. His interests are in the design, synthesis, structure and properties of molecular materials, and his career has spanned many, many aspects of supermolecular chemistry and molecular materials. I've been following his papers for at least 25 years or so. Please feel free to post questions for Jim in the Q&A, not in the chat, in the Q&A as we go along. We'll read them out to him at the end and hopefully have a lively discussion. We are recording the webinar and the recording will be available afterwards. So thanks very much, Jim, for allowing us to do that. So without further ado, Jim, let me invite you to give your webinar exploring polymorphism, co-crystallization and mixed crystallization.
John, thank you very much for your introduction and thank you and Len for making it possible for me to take part in this series. I must say I've enjoyed this series enormously. The quality of the talks has been extremely high. My goal today is to attempt to approach that high level of quality because it's made this a great series. My understanding is that the series has had multiple objectives, but one of the objectives is to underscore the diversity of the topics that are investigated in the field of crystal growth and design, and also the diversity of the people who take part in that field. I'm very proud to be part of a community that has this high level of diversity, both in the subjects being studied and in the people doing the work. Improvement needs to be made, diversity needs to be increased, but this is a field in which a large amount of progress has already been made. So what I want to talk about today is three subjects that interest me, and I hope they interest you. One is polymorphism, the other is the subject of co-crystallization, and the third subject is the subject of mixed crystallization or the formation of solid solutions. I don't have a long talk planned today. I think I have about 30 slides, so I expect to leave time for questions, and I certainly invite them. So I'll start by the basics of polymorphism. If you've shown up today, you're presumably well aware of what polymorphism is. It refers to the ability of compounds to form crystals with different structures with the same composition. And I've illustrated that here with three examples taken from inorganic chemistry. Titanium dioxide, a simple compound. There are four natural polymorphs of this compound. One is the mineral anatase, which crystallizes in a tetragonal space group. Brookite, orthorhombic, and there's also another tetragonal form, rutile. So there are despite the fact that we're familiar with the subject of polymorphism, both in organic chemistry and inorganic chemistry, there are many aspects of this subject that are poorly understood. One of them I'll focus on today in part of the talk is, what are the factors that determine whether a given compound will be highly polymorphic or whether only a few structures are accessible? The other topic is related to the role of computation in guiding research in this area. Crystal structure prediction has made enormous advances in a very short period of time. And I'll talk a little bit about how my group and our collaborators use computation. This has helped identify potential structures. The problem with computation is that it tells you where you might want to look, but it doesn't tell you how you can lay hands on these particular polymorphic forms. So that's another subject I want to talk about today. What I show you here is a molecule that we call ATPH in my group, and I'll tell the story of ATPH a little bit later in the talk. I just want to show you here the structure, and I also want to show you the results of a computational prediction of the different polymorphic forms of this compound that was carried out by Graham Day and his research group in collaboration with us in a project that's ongoing. So what you see on the right here, I think you're probably familiar with this type of plot. It shows relative energy of different polymorphic forms on the y-axis. The x-axis is density. So what you see here is interesting because the forms that we have been able to find for this ATPH compound are marked specifically. We have identified and characterized by single crystal X-ray diffraction 7 different polymorphs of this compound, which is an achievement we're proud of. There are a lot of different polymorphic forms, but you can see from this plot that there's a lot more work that needs to be done to uncover more polymorphic forms. It's well understood that crystal structure prediction over-predicts the number of potential forms, but even if there's a degree of over-prediction, there's still a lot of undiscovered polymorphs in this series. Just to give you a little bit more of a sense of the nature of the challenge, between 0 and 1.7 kilocals per mole, so at this cutoff line, there are over 100 different polymorphic forms that are identified as potential structures. Even within 0.5 kilocals per mole down here, there are 12 potential structures, and nothing tells the experiments how to make these compounds in the laboratory. It's clearly an enormous challenge that remains, to a large extent, unmet. So as a disclaimer, I will begin right away by saying that as a crystal engineer, I have a very mixed feelings about polymorphism. It's a subject of endless fascination. It's good because polymorphism increases the range of available materials that we can study. It's bad because it's going to be very hard to control which structures will be produced under a given set of experimental conditions. In the early years of my work in the area of molecular organization, my group and I focused on how to limit the problem of polymorphism by working with particular types of structures. And the types of structures that we used are characterized by having little flexibility. So polymorphism derived from flexibility was eliminated or minimized as a potential problem. And the compounds also had functionality that caused them to be positioned in a predictable way with respect to their neighbors. So the purpose of this is to eliminate or at least reduce the number of radically different structures that could result from crystallization. So I think you understand this principle. This is what could be called modular construction. There are different names for the topic, but basically it's a strategy that uses structurally well-defined components that are then positioned in a structure, a two-dimensional or a three-dimensional structure by strong directional interactions. These can be hydrogen bonds, they can be coordination to metals, they can also be relatively weak and reversibly formed covalent bonds. So this is the strategy that underlies the extensive area of chemistry that is related to MOFs, COFs, HOFs, and so on. This particular structure is only an example of the type of module from which you can construct hydrogen bonded solids. You can see that it has an enormous capacity to take part in NHN hydrogen bonds. It does that. When you crystallize it, it forms the structure shown here on the right. Just to help you see the relationship between the structure on the right and the individual molecule, I've highlighted one of the molecules in dark blue. So it forms an open structure. About 68% of the volume of the structure is accessible to guests, and desolvation using the technique of supercritical CO2 yields a crystalline porous solid. The porosity in this particular case is relatively modest compared to other crystalline porous materials, but it's important to remember that this compound crystallizes in a way that's basically dictated by relatively weak NHN hydrogen bonds. This is work that was carried out in collaboration with a group of Ashley Howarth at Concordia University, and the reference is down here below. So I don't want to spend too much time talking about modular construction, but in the last few years, we've embarked on a series of studies in this area that involve co-crystallizations that are directed by hydrogen bonding and also by charge transfer interactions. If you co-crystallize hydroquinone and benzoquinone, many of you understand that this pair co-crystallizes to form what's called quinhydrone. So quinhydrone is a one-to-one co-crystal of hydroquinone and benzoquinone. It's historically important because it was the first example of a co-crystal, and it was reported by Friedrich Wöhler in 1844, so it's been known for a long time. The structure is very characteristic and in a sense very logical. So you see here hydroquinone. It forms a hydrogen bonded chain with benzoquinone that alternates. So now we have a new hydroquinone. And the chains stack in a way that's directed by charge transfer. So behind the benzophenone here is a hydroquinone. And so this defines sheets, and the structure is built up of these stacked sheets. Now, these compounds were characterized crystallographically, well, it's about 60 years ago almost, by Sakurai. The idea of using these as modules and controlling the structure by hydrogen bonding and charge transfer does not completely eliminate polymorphism, but as I said earlier, it minimizes polymorphism and makes sure that all of the polymorphs are structurally similar. So the polymorphs in this particular case, there are two of them, and they really differ in the way the planes, these layers are arranged relative to one another. One of the things that makes these compounds topical and interesting today is the fact that they're both redox active. And so if you're interested in redox flow batteries, if you're interested in electrodes composed of purely organic materials that are porous, redox active, then this type of compound is an interesting subject for research. These compounds can also be derived from natural resources, so it's really the motivation for why we began to look at these compounds. So we've extended this considerably, and when I say extended, I mean it literally. We've moved from benzoquinones to these compounds that are called diphenoquinones. So here's a structure. These compounds have actually been known for a long time. This particular diphenoquinone was first reported by Willstetter well over 100 years ago. But the compounds have remained exotic, poorly understood, never examined crystallographically. Information about redox properties is scattered in the literature. The compounds are highly reactive. But when you know how to make them and to crystallize them, they can be characterized in a complete way. And so we've made these compounds, characterize them by single crystal X-ray diffraction, cyclic voltammetry, and many other techniques. And I'll summarize here what we see in this case. This compound forms chains. The chains are held together by CHO hydrogen bonding. The chains stack, and the stacks are related by a sort of a herringbone arrangement with adjacent stacks, as I show you here on the lower left. One of the Diphenoquinone molecules is highlighted in blue. We've extended this work to much more exotic structures, in which, for example, two of these Diphenoquinone units are linked in a spiral bifluorine type of structure. Characterize this compound. Again, it forms an interesting structure held together by CHO hydrogen bonds. Well, back to the subject of co-crystallization. So if you can co-crystallize hydroquinone and benzoquinone, well, what about co-crystallizing a diphenoquinone with a dihydroxybiphenyl? And this works perfectly well. It works perfectly well, and it gives the same type of co-crystalline structure that we see in the classic the quinhydrone motif. So you have here a dihydroxybiphenyl that is linked to a diphenoquinone, which is linked to a dihydroxybiphenyl to form a hydrogen bonded chain. The hydrogen bonded chains stack by charge transfer relationships to give the same type of layered structure that we see in the case of the simplest combination of hydroquinone and benzoquinone. What's interesting about this is that this type of assembly is highly predictable. You can even mix and match. So as long as the two components are not able to undergo a mutual redox reaction, which would complicate the story, you can combine benzoquinones with dihydroxybiphenyls and so on to give very similar types of structures in which hydrogen bonding, charge transfer interactions work in a cooperative way to construct the three-dimensional structure. So that's about all I want to say about co-crystallization for the time being. I'll now move into the subject of polymorphism and why it's something that happens frequently in some cases and not so frequently in others. So the part of the story that I'm going to tell you now is based on work that we did with this molecule called phosphangulene. Phosphangulene was first synthesized by Krebs about 20 years ago, and it's a compound that would interest chemists working in different fields for different reasons. It's a phosphine, so it has an interesting metal coordination chemistry. But from the perspective of a crystal engineer, what makes it interesting is the fact that it has a very characteristic conical shape, which you can see here. You don't have to be a genius in guessing what kind of crystal structure this would give. These conical molecules stack, and that would suggest that at any rate, they stack. Okay, so they stack like traditional Asian hats. The graduate student in my group who did this work is named Elise Heskia, and Elise is a talented chemist, but also likes to draw. So she's done a number of illustrations for the group, including the one of phosphangulene. Now, the curious thing about phosphangulene is that these stacks align the dipole moments, the small dipole moments of phosphangulene, and adjacent stacks align in the same way, which is not necessarily what you would expect, but it appears to be a consequence of the formation of CHO hydrogen bonds between the stacks. At any rate, this produces crystals that are excuse me, in the R3M space group, and they're polar and pyroelectric. Now, one of the things that can be done by crystal engineers to explore molecular organization and why a particular organization is favored and why certain organization is disfavored is to take a structural motif that is encountered and create some kind of obstacle that prevents that motif from being formed. So phosphangulene has this characteristic ability to form stacks. But if you convert it into phosphangulene oxide, or the corresponding phosphangulene sulfide or selenide, you block that stacking. And then the question becomes, well, what does that do? What alternative structures are available to a compound that now has a much different shape, an odd shape that's going to be hard to pack? And the answer is that these compounds form what I will describe as a sort of an offset clamshell pair that's illustrated by the two phosphangulene molecules shown here in red. They can't stack anymore. And the best they can do is form this type of pair in which you have CH-pi interactions that are mutual and help hold this clamshell pair together. So I've illustrated that with this Hirschfeld surface that lets you see a little bit more clearly what the interactions are. It's basically an unhappy molecule from the perspective of packing in a periodic structure. And I would say that this is basically the best that it can do. This unhappiness is illustrated by looking at the fingerprint plots of the Hirschfeld surfaces. And you can see here for phosphangulene that it has a very characteristic, rather compact fingerprint that indicates that the interactions focus on the type of interactions you would have in a stacking of aromatic surfaces with CHO hydrogen bonds. If you look at the phosphangulene oxide fingerprint plot, you can see that it's much more extended, and there's a high density of points that lie at rather large interatomic distances. Which is an illustration of some degree of unhappiness of the structure. It can't find anything that's particularly suitable, and this is the best that it can do. This is not characteristic of what happens when you convert a phosphine into a phosphine oxide. For example, if you take triphenylphosphine, one of the known polymorphs of this compound, and the corresponding oxide, and corresponding Hirschfeld plots are relatively similar. So the conclusion from this is that this is a molecule that doesn't have any good choices. This particular offset clamshell pair can adjust itself in slightly different ways without changing the energy substantially. And that's confirmed by the fact that this is a compound that is highly polymorphic. And in our work, we characterized 5 different forms without really going after the full screening of the different polymorphic forms. It was, a relatively straightforward search. At least would come to me and say, Jim, I've just found another polymorph of phosphangulene oxide. And I would say, well, why are you doing this? I mean, we have other things to do with this phosphangulene and phosphangulene oxide. But she insisted, and she insisted correctly. And ultimately, we came up with 5. I think there are more that could be found if we look for them. The interesting thing is that this is a compound that's highly polymorphic. There are only a handful of compounds in the CSD that are are compounds that are essentially rigid, but are also highly polymorphic with 5 or more forms that are known. And so this is a compound that stands out in the CSD as being unusual. And I think the unusual characteristic is something that arises from the fact that it just does not have any particularly good way to crystallize and can accept a number of alternatives. So I'll come back to tell a similar story about this ATPH. That's a compound I showed at the beginning of this talk. I didn't explain why we were interested in it, but I did show you that it has a very high density of potential crystallographic forms. If you look at this compound, you'll see immediately that it has a very high ratio of nitrogen to carbon and a large number of NN bonds. So you would say, this is not a compound I want to make on the kilogram scale and store in my laboratory. And in fact, it is a very close relative of compounds that are being developed as lead-free primary explosives. We have not made this compound detonate, but it is highly sensitive to decomposition. And so we've never made it on a scale of more than about 5 grams, and we take full precautions in working with this compound. The synthesis is relatively straightforward. You can make at just by taking dichlorothalazine and doing substitution with azide. One of the substituted azides cyclizes in a characteristic azide tetrazole isomerization. You can also make the compound by diazotization with corresponding dihydrazine of thalazine. It's interesting that the preferred structure of ATPH is this azide tetrazole and not the diazide or the bis tetrazole. We've done computational work that suggests that that is something that you can explain on the basis of the interaction of these two groups. What makes ATPH surprising is that it is also a purported natural product. This is really astonishing. It was isolated, and here's the report is this 1985 paper. It was reported to have been isolated from a culture of Gymnodinium breve, which is a toxin that is associated with red tides. There's a toxin producing dinoflagellate associated with red tides in the Gulf of Mexico. If you look at the dictionary of natural products, it's the only one that's an azide or a tetrazole, the only one reported to be explosive. So it's a compound that calls attention. An organic chemist who sees this in the dictionary of natural products to say, where in the world did this come from? It is definitely an effective poison for fish. The 100% lethal dose is only 400 nanograms per milliliter. So there seems to be some connection with the interest of this compound as a toxin. Now, the other thing that's interesting, and it was totally unexpected when we began to examine ATPH, is the fact that the compound is highly polymorphic. Again, like phosphangulene, despite the fact that the structure is relatively simple, nearly planar, and conformationally basically inflexible. You can have rotation around the CN bond of the azide group, but in fact, in all the polymorphs that we see, the angle of rotation is between 0 and 10 degrees. So this structure here represents the preferred conformation of this compound, and the azide group is very close to the molecular plane. Despite this fact, the compound is highly polymorphic, and up to this point, we've characterized by single crystal X-ray diffraction 7 different forms, which are compiled here in this particular table. The question is, well, what is it that accounts for this very high level of polymorphism? And so we began to examine this from the perspective of looking at the crystal structures and trying to understand how they differ and why they differ, and what those differences may tell us about the origin of polymorphism. So I've only shown you 2 structures out of the 7 on this slide. On the left here is form 3, which is an FDD2 crystal that we get from isopropyl acetone. Again, I mean, as I said before, the conformation is essentially planar. There are many different NN and CHN interactions involving the tetrazole, the azide group, and the 4 CH hydrogens of the compound. The packing in this particular case is herringbone, and that is also the case with forms 1, 2, and 5. So roughly half of the structures adopt this type of herringbone pattern. The other half, and illustrated here by form 4, crystallized from ethyl acetate, again, essentially planar, again, many NN and CHN interactions, but the packing forms sheets. So there is a striking diversity in the different types of forms that can be produced by the crystallization of this relatively simple molecule. This is interesting because in the field of explosives, there's a general consensus that explosives that have a layered packing are less sensitive to impact than structures that have a herringbone pattern. And this appears to arise because if you subject a compound that's layered to an impact, the layers can slide over one another. And in the herringbone case, molecules are forced into one another. But although this makes some kind of intuitive sense. It is a conclusion based on comparing materials that have different compositions, not just different structures, but different compositions. And so the possibility of working with compounds like ATPH to explore how the impact sensitivity of a single material, a single composition, reflects how the molecules are organized is an interesting possibility. We haven't done that yet, but the potential is there. So again, the conformations of the molecule and the different structures are essentially the same. So the high polymorphism is not a reflection of high flexibility. But what we see in examining the crystal structures is that virtually every atom of nitrogen and every CH bond can take part in NN or CHN interactions. So what that tells us is that however the molecule is arranged, it's possible to construct the type of key interactions that help hold the structure together. So it's an assessment that says, again, that you can position these compounds in different ways. You have enough interactions to hold it in that orientation, but no driving force that directs it away from that organization towards something of substantially greater stability. So that's sort of an assessment that's highly qualitative. It's based on looking at the crystal structures, and it can be supported to some extent by quantitative measurements such as an analysis of Hirschfeld surfaces. You can see from the chart here that there are a large number of NN and CHN contacts in all the structures. In fact, these contacts contribute 55 to 70% of the entire Hirschfeld surfaces. At least this is only 5 of the 7 forms. We left out one because it's form 2, because it's a low temperature form related to form 1, and we left out form 7 because it has Z prime equals 4. So we limited the cases, but basically in all the structures, this generalization is true, that these NN and CHN interactions are legion. Also, by comparing form 3, which is herringbone, and form 4, which is a sheet structure, you can see here that the Hirschfeld surfaces, either filtered or unfiltered, are very closely similar. So again, this molecule can do all sorts of stuff without really changing the ultimate story. So we wanted to look at this more carefully to see if our intuition as structural chemists was supported by theory, by crystal structure prediction. So Graham Day and his group have taken a look at ATPH, and this is the same plot showing the potential crystal structures that I showed you early in my talk today. So again, there are over 100 possibilities within 1.7 kilocalories per mole of the global minimum, and there are 12 different possibilities that lie within 0.5 kilocalories per mole of the relative energy. This initial crystallographic crystal structure prediction plot was based on a fairly straightforward force field. I describe it here a little bit, and if you're interested in the details, you can look at the eventual paper. But it's limited, just for those who have a sort of a specialist interest in this, to the 25 most common space groups with Z prime equals 1, and the 5 with most common with Z prime equals 2. So it's a good look at the potential structures, but not entirely complete. The structure is extremely dense. So density is consistent with the fact that carrying out a year-long devoted polymorphic screening exercise, we've already generated 7 different forms. And so that's consistent with the idea that this is a compound that is disposed to high levels of polymorphism, and that disposition is a consequence of the ability to form multiple NN and CHN interactions. So this is on the left here is the initial force field level crystal structure prediction plot. And you can see, I mean, there are a large number of different possible structures here, all within a very small window of energy. And that certainly raises the question of whether or not at this particular level, the predictions can be considered to be accurate. And so Graham and his group carried out a re-optimization using density functional theory to explore what would happen to the number and order of possibilities in this narrow 0.5 kilocal per mole window. And the good news is that here's the result of that reordering. It still indicates a high density of potential forms. All of the forms that we have observed experimentally match structures that are predicted to exist. Now, that's good news. And the other good news is that of the 6 structures predicted to be the most stable, we have already found 4 of them. So what this means is that the crystal structure prediction is good, and the experimentalists doing the search for the different polymorphic forms are good too. So everything seems to match quite well. The predicted order of stability places form 5 and form 4 very close together. Now, you would not necessarily be reassured that you have identified the global minimum from this, but theory says that they should be very close together. And so we did, we were able to develop conditions that produced all of the forms in essentially phase pure forms. So we were able to characterize them by all the different available techniques and carried out various experiments to compare their stabilities. And basically form 5 turns out to be the most stable, slightly more stable than form 4. So now I'll turn to the subject of mixed crystals or solid solutions. So as you presumably know, this is a crystalline structure that results when multiple components occupy essentially random positions in ratios that can be varied continuously over a certain range. Now the question is, what are the rules that determine when a molecule can replace another one in a crystal lattice in this way? And these rules are not clear, but the answer to the question of what are the rules is an important one, because it has practical implications in a number of areas. Can you dope a structure with another component? Can you use crystallization to purify the compounds? If you can make mixed crystals, you can also make materials with continuously variable properties. So there are lots of reasons for probing this phenomenon of mixed crystallization more than it's already been probed. A lot of the early understanding comes from the work of Kitagorowski and his school. And I think the impression that this work gives is that mixed crystals with continuously variable compositions require that the components crystallize isostructurally. So they have to be similar enough to crystallize in essentially the same way. But more recent results suggest that those rules can be relaxed somewhat, and the work I'll tell you about today supports that conclusion. If you're interested in the subject of mixed crystals, I strongly recommend looking at Matteo Lussi's review on the subject. I think there are a couple of them, but this one will certainly give you a good acquaintance with the with the field and the current state of the art. So we began this work by looking at a particular system, a very simple system, but a system with the potential to shed light on mixed crystallization and the rules underlying mixed crystallization. And the compounds that we studied included dibenzo thiophene and dibenzofuran, very closely related compounds. Dibenzothiophene has a single reported polymorph, a P21 over N structure, and dibenzofuran, one reported polymorph, PNMA. These compounds have been crystallized under multiple conditions and have been known for a long time. And these are cases in which only one polymorphic form had been reported. The structures are certainly related. Show you pictures here. There are herringbone interactions, stacking arrangements. They're not easy to describe, but they're related. The signature of a dibenzothiophene crystal is the formation of an elongated needle, whereas dibenzofuran crystallizes in flat plates. So you know when you crystallize compounds of this type, what you're getting just by visual inspection, but I'll have more to say about that later. It also turns out that fluorine and carbazole crystallize like dibenzofuran in the PNMA structure. So this makes the story a little bit more interesting and a little bit richer. We started out this work by attempting to form mixed crystals of the thiophene and the furan, and we succeeded. We characterized a large number of these mixed crystals by single crystal X-ray diffraction, and we found that it was possible to get mixed crystals with continuously variable compositions over a very wide range. So if you look at the table here, you can see that we obtained crystals that have the thiophene 23%, furan 77%, up to crystals that contain 80% of the thiophene and 20% of the furan. What is remarkable about this is that this range of compositions can be attained despite the fact that the two compounds do not crystallize isostructurally. The other thing is that over this entire range, the crystals are always the PNMA structure of dibenzofuran. This is unexpected because it means that even if you replace the smaller furan by the larger thiophene, 80% in fact of the thiophene, you still get crystals forming in the furan structure. So these compositions, there are lots of things about mixed crystals that you could ask. I mean, one is that in a given batch of crystals, there were small variations from crystal to crystal, but by and large, the composition of the crystals reflected the feedstock that was used, and the composition of the crystals remained constant. We did this by selecting various crystals and examining unit cell parameters, in some cases solving the crystal structures. What I'm telling you about the thiophene and the furan also applies to the thiophene combined with the fluorine and carbazole. So there's the possibility of preparing mixed crystals with a wide range of different compositions. The compositions of individual crystals were determined by X-ray diffraction by refining the occupancy of oxygen and sulfur and confirmed by Raman spectroscopy. So the compositions are solid. What I show you here is a plot of a Vegard law type relationship that shows the unit cell volume of the single mixed crystals as a function of mole fraction of thiophene. So again, these two materials are not known to crystallize isostructurally. Yet the composition can be varied continuously over a wide range, and the unit cell volume follows a linear Vegard law type relationship. So down here is the dibenzofuran structure. Here are the plots of the unit cell volumes of single mixed crystals, and here is the known P2 structure of the corresponding thiophene. So it lies off the plot. It's a different structure. In fact, it's a more stable structure than the other one because it's more dense. The interesting observations. So again, we teamed up with Graham Day and his group to probe this using the methods of crystal structure prediction, and the results are preliminary. This is not the finished work, but you can see here on the left the predicted structures for the thiophene. The P2 structure turns up in the search. It is not the global minimum. There's another structure here that we have never seen, even after looking at this quite a bit. I don't know whether this is a real structure or not, but it any rate, it's there. And the same thing is essentially true for the dibenzothiophene structure. There's a match with the observed reported structure, which also turns out to be the global minimum. So there's a clear challenge in this work. I mean, this faces the experimentalist with the potential existence of many different polymorphic forms, but the experimental evidence is that the thiophene crystallizes in this form and the furan crystallizes in this form, and nobody's seen anything other than that. How do you get these other structures? The unfortunate thing is that you can see from this prediction that if you put the furan into the thiophene structure, it matches one of the predicted structures, but it's 4 to 5 kilojoules less stable. And if you put the thiophene into the furan structure, you find it as a predicted structure, but again, it's highly unstable relative to the global minimum. So what can you do to solve this problem? Well, what we did is something that's been used occasionally, and it was turned out to be surprisingly effective in this case. We developed a system. Basically, you see here a tube, and in that tube we wedged a crystal of the corresponding furan, fluorine, carbazole, or mixed crystals containing thiophene and these other components, and then applied vacuum to this tube that we allowed to draw in vapors by heating the thiophene. And if you look at this carefully, you can see something. If you remember the initial pictures I showed you of the crystals that are characteristic of the thiophene versus crystals that are characteristic from the furan, you can see a cluster of needles here. Those are the regular form of the thiophene, but all these flat plates out here, these are the new form of the thiophene that have been induced by crystallizing on surfaces of the PNMA structure of whatever the seed is. And so we were able to extract these crystals, solve the structure, confirm that in fact it was the PNMA form of the thiophene, and showed that the unit cell volume lies close to the predicted Vegard's plot relationship. So it's an interesting story of how a potential polymorph could be obtained by in a directed way, as long as you're willing to apply a proper effort. How am I doing on time? Yes, we're okay.
Yeah, keep going, Jim.
Okay, so this is related to work that we published a couple of years ago related to Roy. And I guess, maybe some of you have seen this work, but Roy is famous among people interested in the subject of polymorphism because it is currently the most polymorphic compound reported in the CSD. So this is obviously limited to materials that are characterized by single crystal X-ray diffraction. So it's an interesting compound. Again, these questions of where does the high propensity to form different polymorphs come from exactly in the structure? We were interested in exploring that, and we thought that one way to explore this question would be to make compounds related to Roy, but with carefully selected differences. And we fixed on furoy, the corresponding furan shown here. So this is connected to the work that I just told you about with dibenzothiophene and dibenzofuran. So we said, well, if Roy is highly polymorphic, then there is no reason to expect furoy not to be similarly predisposed to forming polymorphs. And in fact, it does. We've never made a thorough screen for different forms, but we quickly found several forms, and that confirmed the feeling that it would also be a compound susceptible to high levels of polymorphism. The different polymorphs, for the same reasons as Roy, have different colors, so it's proper to call it furoy. The forms that we found initially turned out not to be isostructural with forms of Roy. So this is a very similar situation. Two compounds that are not known to be polymorphic, where there is likely to be a substantial difference in stability, we began to use these Roy crystals to seed the crystallization of Roy by using melts of Roy. None of this worked with the initial crystals of Roy, and conversely, using crystals of Roy to seed the crystallization of Roy from melts was not successful. But we eventually found that the mixed crystals of these two compounds had an effect on the crystallization and led us to new crystal forms of Roy itself. That offers a suggestion that there may be something special about mixed crystals. And this needs confirmation, but our working hypothesis is that mixed crystals have surfaces that have a composition that's similar to that of the target compound, but some differences in the arrangement of the molecules that may allow them to have the effect of heteroseeds with different compositions and different arrangements. So that needs to be tested. Just one quick test that's ongoing in my group. This is a subject of considerable interest to the pharma industry, and right now my group is working with different players in that industry to see if we can find new crystal forms of pharmaceutically active compounds that are on the market. And I can't talk about that work, but I can talk about something that I don't think has strong commercial implications, but illustrates the potential. We began to look at salts of paraquat, the dimethyl viologen compound, the dication that's shown here. In the work we did with Feroy, we had to invest a lot of time in making Feroy itself. It was not a trivial synthesis. And so you may think, well, using these analogs as heteroseeds or forming mixed crystals, that's a lot of work. But in fact, about half of active pharmaceutical ingredients are formulated as salts. So there's the possibility that instead of actually making an entirely new compound, you can just replace the biologically inactive ion and start making mixed crystals and exploring the use of these mixed crystals in that way. And we've tested that with paraquat. Paraquat dichloride turns out to be one of the most widely used herbicides in the world. And even in the US in 2017, it's just this 4 million kilos of this compound were used as an insecticide. There are different crystal forms. So there's an anhydrous chloride, there's a dihydride, but there's a standard monoclinic P2(1)C trihydrate form. And we've shown that form allows us to make mixed crystals containing a 1:3 ratio of bromide to chloride. So bromide is introduced at a certain level. And we've been able to use those mixed crystals to seed the crystallization of the dibromide in the same, in a form that had not been reported before. So that tends to suggest that this use of ionic analogs may be an effective solution to the problem of the need to avoid complicated syntheses. I should add that in the farm industry, a lot of analogs are already available. So the use of this, of structural analogs as seeds or in the formation of mixed crystal seeds is not as complicated as it might appear to be at first. So let me bring this to a conclusion. I have some final comments to make that I reflect my own experience in the field, may be interesting to you. First of all, I said before that crystal structure prediction has made astonishing advances. I mean, my perspective is that of an experimental scientist, but it's impossible for me to do good work without making full use of crystal structure predictions. It's also important to be able to use the data that are collected in the CSD to guide research. But I would make the point that the use of these tools needs to be complemented by carrying out parallel experimental studies in which someone has synthesized and specifically designed compounds to test principles of molecular organization. This is something that you need to do to find out where the areas of potential lie in this vast realm of different structures that can be produced. And I don't think that theory now, either using computational methods of crystal structure prediction or augmented by artificial intelligence, is going to replace good chemical intuition for a while as a way of directing you to places that you should be looking. But you know, I'm perfectly happy to debate that particular subject. Mixed crystals are promising materials. I found it really interesting to study them, and clearly more work needs to be done to clarify the rules under which they can be formed and what they can be used for. I said at the beginning of my talk that I'm very proud to be part of a community of researchers who study so many different interesting things. I've learned a lot from all of you. This is a field that has pushed my own research group in so many new directions, into theory, into using different spectroscopic techniques that we never used before, into looking at the details of how you characterize different solid forms. It's been a fascinating adventure, and I thank you all for being part of it. And finally, I comment about crystal growth and design. This is definitely unpaid publicity, but I'm deeply grateful to the journal for having served this community of researchers and unified them. I mean, it's been over 20 years, but you know, crystal growth and design has become a place where I certainly feel comfortable publishing myself. I know the community and what it's interested in. And in particular, the series of webinars has been a great gift to us. I don't know if the rest of you are like me, but I'm in a chemistry department that has evolved over the years, but it still has a somewhat disciplinary organization to it. So I'm trained as an organic chemist, but if I want to talk to people about crystal engineering, I have to persuade my organic colleagues that, yes, this is interesting to you. Here I find my community. It's been great. This webinar series is an illustration of that. These webinars have been more interesting to me than if my colleagues are listening, I apologize, but I find this webinar series has been more interesting to me than many of the departmental seminars. Because they've been focused on important issues and have taken us away from well, have given us an opportunity to keep doing science under circumstances that have not been ideal for the last couple of years. So thank you for that. And that's it. I will conclude this by acknowledging the members of my group who've contributed to what I talked about today. Their names are listed here. I've talked a little bit about Elise, but it's a creative group. I'm deeply grateful to all of you for your contributions. None of this work would have been possible without the very talented contributions from Thierry Maris, the departmental crystallographer. I've mentioned that Graham Day and two of his students, Joseph Arnold, Joshua Dickman, have been involved in the computational predictions. Radu Iftemi has done computational work that I don't think I really mentioned too much in this talk. Ashley Howarth has collaborated with us in the study of different aspects of modular construction, along with her student, Svarta Joyan. Support has come from NSERC in Canada, the Canada Research Chairs Program, the province of Quebec, what's called the Canada Foundation for Innovation, which has provided world-class infrastructure. It's one of the reasons why I've been here for 40 years. And collaborations with industry through Admeri Bioinnovations and MyTax. So again, thank you for giving me a chance to talk. I'm happy that that you came to the talk today. I hope I've said something of interest to you, and I welcome your questions. Thanks.
Jim, thanks ever so much for a fantastic talk, really interesting, and thanks for the kind comments on the journal as well. Len and I have been here for all the talks, and we've certainly really enjoyed them, so I'm glad you have too. We're a little short on time, but perhaps you'll spare us an extra few minutes to answer the many questions that are coming in. We've had lots of people here and lots of questions, so without further ado, I'll get stuck in and see how many we can get through. Question that's been pending for 40 minutes or so. Gujan Gupta says, I was wondering if any of the hydroquinone crystals would crystallize in polar space groups and thus perhaps become ferroelectric?
Have not looked at that yet, but that's a point that interests us. I think our primary focus is on crystals that we could use. We're interested in combining the properties of porosity and conductivity and redox stability. So the other aspects are a little bit away from that primary interest, but it's an interesting question.
Great. Okay. And Manad Chakravarti says, does phosphangulene fluoresce with its rigid structure? You'd think that it would emit in the solid state.
We have not observed that. We've not looked for it.
Maybe the phosphorus.
I'm not familiar with that property of I'm not sure that that's something I associate with aerophosphines.
Yeah, something to look at maybe.
Mm-hmm.
Okay, and Kao Lee has a keen eye on slide 13. They've noticed that polymorph 6 has a goof of 0.03, and they wondered if there was any issue with that. Might be typo or something. I don't know. Do you want to comment on that or look later?
Let me slide 13.
It's maybe a little fine grain for the audience. Maybe just a typo, Jim.
Yeah, that can't be true. Thank you for pointing that out. This is a manuscript that's undergoing review right now. So I talked about a lot of stuff today that wasn't published. So one of the advantages of presenting that to an audience as sophisticated as this one is that they will come up with points like this. I'm very grateful for that.
Some free extra refereeing. Okay, Manab Chakravarti has another question, which is a much more general one. Can polymorphs have the same space group but different packing patterns? And I think I know the answer to that, but I'd be interested.
No, absolutely, that's quite true. I mean, titanium dioxide is a great example of that.
Yeah. Okay, another general question. If any polymorph is identified with a solvent molecule, how can we differentiate between solvated form and polymorphs? So I guess this speaks to the definition of pseudopolymorphism again.
Yeah, well, I obeyed very strictly in this talk the distinction between polymorphs and pseudopolymorphs. So all the polymorphs I've talked about only contain the molecule that I described. I left out anything that we may have observed about solvates. I mean, with the exception of the structure of the hydrogen bonded triazine, which is obviously an open structure with many molecules of solvent included. All of the others are unsolvated systems. We haven't looked. So if I said something about polymorphism, I'm not referring to any of the solvated forms.
Right. Exactly. Okay, question from Ashwini Nangia on ATPH. The planar conformation in which the azide group flips over to the other side will have an intramolecular CHN hydrogen bond with the phenyl CH donor, but you don't seem to observe it in any of the polymorphs. Computationally, how different will these two rotamers be in energy?
Ashwini, thanks for being here. I wish we were in the same room together having a chat about crystals. Look, I mean, that's an interesting question. We calculated rotational barriers for that compound, and the form that is shown on this slide here, where the azide points away from that, is by far the most stable form. We never saw any structure in which there is a substantial rotation of that group toward the CH. And I mean, I think that's reasonable. I mean, the 1,8 disubstituted naphthalene systems have similar conformational preferences. I mean, that's why I insisted that in all of the different polymorphs, this compound adopts essentially the same the same molecular structure. And in the azide is close to the plane. In the initial crystal structure predictions, that created an issue because that was based on a model in which the azide group was in the plane and the dihedral angle was 0. Some of the polymorphs have a slightly non-zero angles ranging up to about 11 degrees. So that's why some of the DFT reoptimization reordered the different energies.
We're over time. Do you want to carry on for another couple of minutes, Jim? There's quite a lot of questions.
I'm happy. I'm yours. I mean, you know, look. I'll stay as long as you have.
You'll talk science as long as you're allowed to. Huh?
I mean, this is such a great opportunity for all of us.
Yeah, well, there's certainly loads of questions. We won't get to them all, but if it's okay with you, let's try a few more because it is pretty fun. Ashwini has another comment here on DBT, just a detail. Are both the known P21 upon N structures and the new higher symmetry PNMA polymorph fully ordered, or is the PNMA form having some partial disorder?
I don't see anything conspicuous in the crystallographic data that indicates any degree of disorder. I think once that crystal form is produced, it's metastable. I mean, you have to do the analysis without waiting for weeks, but it doesn't seem to be disordered. You may notice that if you look at the Vegard law correlation for that compound, it's slightly off the line. So there may be some problems there. I haven't really put my finger on what that indicates. I don't think that disorder is an issue.
Okay, and the obligatory Travis Holman question. Lovely talk. The mixed crystal work's inspiring. We've encountered in my lab, this is Travis's lab, some complicated crystal forms of chiral compounds grown from solutions of various enantiomeric ratios. So, for example, a complicated 4R3S phase. He doesn't know how much this has been studied. Have you considered studying this sort of phenomenon? I guess non-stoichiometric mixed enantiomer crystals, so non-racemic.
Travis, hi. It's again, I'd say the same thing to you as I'd say to Ashwini. I'm sorry you're not here. You've always got the interesting perspectives on things. Look, I mean, we have our hands full with all the stuff that we're doing right now, and adding chirality and stereogenic centers to the mix is something we haven't dared to do so far. I'm interested in going in that direction, and we have a pending project that would look at mixed crystals related to sugars. So that's going to get us into this particular question of, I mean, but this has been looked at. You know, it's just a general subject that's been looked at by other people in terms of, you know, to what extent you can mix. I mean, you talk about racemic crystals and conglomerates, but you know, you don't necessarily have to have a particular ratio. You can get mixtures that vary considerably. So the subject of mixed crystal, the rules governing the mixed crystals formed by enantiomeric compounds still need to be written. There's much to do there, but it's not a subject that's completely neglected either.
Okay, I'm just skipping to perhaps the ones that are a bit more specific. So, Lee Englert asks, maybe I can ask whether rigid compounds such as FANG-O, which come in different polymorphs, also tend to form different solvates. Is there a correlation between number of polymorphs and number of solvates, I guess?
Yeah, that's a very good point. So if a compound is unhappy and unable to pack effectively, then you would also expect it should be susceptible to forming pseudopolymorph solvates. And in fact, that is the case. It's also a compound that is very susceptible to forming mixed crystals. Again, I would say for the same reason. So you can easily replace phosphangulene oxide with phosphangulene sulfide. So again, this is a substitution that replaces a small molecule by a larger molecule, and the only way that you can do that is if the packing efficiency is low. So yes, all these things I see as correlated events.
Okay, maybe we'll have one last question from an expert crystal structure calculator, Sten Nilsson-Lill, who says, for ATPH, you had chiral space group in some cases. Is it due to helical chirality? And secondly, did you or Graham look into the free energy landscapes?
Yeah, that's a subject that is of ongoing interest, because once you put the azide unit out of the plane, you now have a chiral unit. So that did not come up in the initial force field level calculations, but would come up later. So those are issues that are still need to be looked at more carefully.
Great. Okay, well, we're 10 past, so perhaps we better call it a day then. But I think you can see, Jim, from the vast numbers of comments and questions that have come in and are still coming in, that your talk generated a tremendous amount of interest in this community, and from the vast number of attendees as well. This has been one of our largest and most enjoyable webinars. So thanks so much for coming along. We really appreciate it.
Great. As I said before, I've only built on the success of my previous speakers. I mean, it's a series that has legs. You should continue this long after COVID has disappeared from the land. So yeah, it's been great. Thanks very much, and thanks all of you for attending this morning, or whatever time it is, wherever you are. Thanks. Hope to see you in person.
Great. Thanks a lot, everybody, for coming along. Yeah, I think we definitely will keep the series going. It's one of the things that Len and I discussed right at the beginning, that we could make something that went beyond the COVID pandemic and actually became a way to use these new tools that we've all learned to do something lasting. And certainly there's no letting up on that. I think Len would agree. Okay, well that's it for today, folks. We'll see you all next month for Franziska Emmeling's talk. And until that time, thanks very much.